Welcome back to Physics 371 Online. Now that we've learned a little bit about how magnetization is produced and what types of magnetization an object can have, let's just assume that we have an object with a magnetization M, and we'll focus now on concentrating the magnetic field this produces in the region around it. So we start by defining magnetization more carefully. Magnetization is defined for a solid object as the dipole moment per unit volume in that object. And of course it's something that can vary in space. It isn't necessarily the same everywhere. The magnetic vector potential of a single dipole M, we've already learned how to calculate this, and it's given by this familiar expression that we learned at the end of chapter 5. Now, in a magnetized object, each volume element, if we divide it up into infinitesimal elements, has a dipole moment, because if M is the magnetization within the object, then the dipole moment per unit volume times a volume gives you the amount of the dipole moment at that location. So what we can do by subdividing this magnetized object into little pieces is we can calculate the total vector potential at a point P as follows. We can use this familiar geometry where we've got this solid object, we've divided it up into little volume elements d tau, so m d tau gives us the dipole moment, and then we can write down the overall A at a point P in the vicinity of the object by simply integrating the expression for the dipole over the volume of the object, and we've replaced little m with capital M d tau. So it's exactly the same integrand as what was up here in the dipole term for the vector potential. Now we're going to use a little bit of vector algebra and some vector calculus to rewrite this expression in much the same way that we did earlier for the electric potential of a polarized object. You'll remember back in chapter 3, at the beginning of chapter 4, that was how we proceeded once we learned what polarization was. So now, having learned what magnetization is, we'll go ahead and expand that integral expression for the vector potential using a simple identity that we actually proved as a homework assignment back in chapter 1. The gradient of 1 over this script r quantity, which is the distance between the element of dipole moment and the point in space, is just script r hat over the distance r squared. And as a reminder, this involves differentiating with respect to the source coordinates, which in the previous diagram I showed was the r prime coordinates, the coordinates that locate a point within the polarized or the magnetized object. So with this identity, we can go back to the original expression for A that was an integral over the volume of the magnetized object and replace r hat over r squared with the gradient of 1 over r. So what we have in the integrand now is m cross gradient of 1 over r integrated over the volume. Alright, now this actually might look familiar to us because in one of the product rules that's inside the front cover of the textbook, we have something that looks like that. We've got a vector quantity crossed into the gradient of a scalar quantity. And so that's what's in this integrand, and that's actually the term that's on the right-hand side of this product rule. If we take the curl of the product of a scalar function f and a vector function a, we get f times the curl of a minus a cross the gradient of f. So if we identify the a and the f in this equation, where a is the magnetization and f is the scalar function 1 over script r, then this product rule becomes as follows, right? F is 1 over r, a is m, so now we've rewritten it in this form using the terms that are in our expression for a, and notice now that what we've got in the integrand for a, the m cross gradient 1 over r, is on the right-hand side of this product rule. So if we solve for that, then we get an expression here that we can substitute into the integrand so that we can rewrite a in a different form. So the vector potential expression that's up here with this substitution, where this term is now, these two terms are being substituted into the integrand, becomes A is mu naught over 4 pi times two different volume integrals, the integral of the curl of m over r hat d tau minus the integral over the volume of m cross the gradient of 1 over r. So it doesn't seem like we've made progress, and yet if we look at these two expressions carefully, they should remind us of something that we've seen before. But we'll get there in just a moment, because first we have to do a little bit of work with this second volume integral to rewrite it in a different form. The second integral can be replaced by an equivalent surface integral, and I won't show you the details, but this comes from a very simple extension of the divergence theorem. So what happens is this second term is going to get replaced by a term that involves a surface integral. So this is the volume of the magnetized object, and here we're integrating over the surface which forms the boundary of that object. And notice that this integrand here is replaced by this term where there's a minus sign in the surface integral. So minus the negative gives us a positive. So that if we now write out this expression and write the two terms out separately, multiply the mu naught over 4 pi out, we get mu naught over 4 pi times the volume integral plus mu naught over 4 pi times the surface integral. And now take a look at these two terms, because they ought to look a little bit familiar, especially if you see that they both involve the integral of some kind of quantity over script r. And where we've seen this before was in the expressions for the vector potential resulting from two different kinds of current densities. The first one being a volume current density, such as you might have in a thick wire, and the second one being a surface current density that you might have on a sheet, a conducting sheet. So what we've got, the first term looks an awful lot like this expression if we substitute J for the curl of m. And the second expression looks a lot like this term with the surface current if we substitute where it says m cross dA, if we make that k dA, then we get the same thing. And yet it's kind of odd because we've got a magnetized object. We're not talking about any current flowing in it. We're not connecting it to a battery, for example. And yet we see these two terms which give us the vector potential associated with this magnetized object. They behave as if they were a certain kind of current. So we can recognize what we've just been saying is that we've recognized in a magnetized object there's the presence of an effective current density in these two terms. So if we make the identifications that I just talked about, we write the first term as the integral of 1 over script r times a special kind of current density, and we'll call it J sub b. And this stands for bound. It's a bound current density. And so it simply replaces the curl of m in the expression for A above. So JB is the curl of m. Yeah. So JB is the curl of the magnetization vector. In the second term, okay, the KB dA plays the role of m cross dA, and you can see with just a little bit of work that KB can be defined as m cross n hat, right? Because the dA vector in the expression up here could be written as n hat times the scalar dA, right? So what we now have, what we've realized from analyzing this expression for the magnetic vector potential of a magnetized object is that it can be understood as arising from the contribution of two special kind of current densities. And we'll call them bound currents for now. I'll explain why in a few minutes. Now, what good is this? I mean, how can this be useful to us if we're trying to find the field of a magnetized object? Well, here's how it goes. If we know the magnetization of the object, let's say someone tells us they've taken an object, subjected it to an external field, and the object now is magnetized. So if we know that magnetization, we can calculate these bound current densities, right? Because JB and KB both depend on M. And from these bound current densities, we can get the vector potential And from the vector potential, we know that B is just the curl of A. So in principle, from the magnetization, we can then find the magnetic field in the vicinity around the object. But even better, if the current densities, these bound current densities, JB and KB, if they have certain symmetries, then we can often directly find the magnetic field using Ampere's law. And if that's the case, we don't even have to calculate the vector potential at all. We can go directly from these highly symmetrical currents to the magnetic field. So if that works, it's going to simplify the process a great deal. But okay, before we do some examples, and we'll do some of those in class, what do these bound currents mean physically? Right? Why do we call these bound currents at all? How can a current even be bound? Because a current seems to imply the flow of charge, so why would you call it bound? Well, let's look at a very simple schematic diagram. Imagine here an object that's magnetized, okay, and internally what that means is it's got many tiny magnetic dipoles which can each be thought of as a tiny current loop. And here I've shown an object where the magnetization vector would be pointing out of the page because the fingers of the right hand curl around in the direction of these current loops and the thumb points out of the page. So here's a magnetized object. Now, if you think about the superposition of all of these tiny current loops, what you notice is that in the interior of the object, these adjacent current loops tend to have currents that cancel each other out. Maybe not completely, but at least they have opposite orientations. So if the magnetization might be changing within the volume of the object, these two adjacent dipoles, or these two adjacent current loops, will tend to cancel each other out. They will produce a net current that's the sum of these two, and the tendency is for them to cancel out. So then internal to the object there will be some sort of current that is simply the superposition of all of these current loops. And then the other thing to consider is the surface, because at the surface, the current loops that are at the surface don't have anything to cancel them out. And so there will always be a net current flowing on the surface of this object as a result of the magnetization. And these are the bound currents that we're talking about. So schematically we can think of the object now as having some type of a surface bound current which will flow in the example shown here in the counterclockwise direction, right? And I'll draw it just inside the surface, right? It arises from these current loops that have nothing to cancel them out at the surface. So it's a closed current path, KB, that's just inside the surface. And then there's going to be, as I said, some partial cancellation of adjacent current loops, but maybe not complete cancellation. So the interior of the object will have some kind of what could be a very complicated volume bound current density. So KB is a surface bound current density, JB is the volume bound current density. And I'll just mention here that if the magnetization is uniform, in other words, if the magnitude of the current in each of these loops is the same, then JB will simply be 0. And that makes sense because JB is the curl of M. And if M doesn't vary in space, that won't have any curl, and JB will simply be 0. So that does happen for a uniformly magnetized object. And in that case, you would simply have the surface current, bound current density. All right, so this diagram again is showing the object as consisting of a volume bound current and a surface bound current density. Okay, so finally, why do we call them bound? Well, the currents are bound in the sense that they come about from the superposition of many tiny current loops. And the point is that each of these tiny current loops is bound to a parent atom. The charges, or the electrons that make up these loops, never move from atom to atom. They stay bound to the parent atom. So what we express as these bound current densities come about as the superposition of the motions of many charges. None of the individual charges follows the entire current path. For example, there's no charge that follows the whole surface current path of this case of B. And whatever JB looks like, there's no single charge that ever follows it completely within the volume. Okay, so that's why we call them bound currents, even though it might sound somewhat paradoxical. Clearly now we need some examples. We need to go back to the expression here for A. We need to show, if we know the magnetization, how to calculate JB and KV, and then if they have the right kind of symmetry, how to use Ampere's law to find the field. And that's what we will do next class period. I'll see you there.